This video lecture is meant to further explore electron configurations for some elements that are a little more complex than the elements we've seen previously. You've made orbital diagrams for elements in the first three periods of the periodic table, but today we're going to take a look at the orbital diagrams and the electron configurations for the elements of the fourth period. Here's an interesting periodic table that's been shaded into four different blocks. The first two columns and helium are shaded light blue. These two columns represent the S block because those elements are in the process of filling up the S orbital. Over here to the right in green are the P block elements, and these are elements that are working on filling up the P sublevel of whichever principal energy level they happen to fall in. So for example, carbon is in the P block, so carbon will have electrons, 2 electrons, because it's the second one over from the left. It'll have 2 electrons in the P sublevel of the second principal energy level. How do I know it'll have 2 electrons? Because it's the second one over in this block. How do I know that those electrons will be in the P sublevel? Because this is what we call the P block. How do I know that those electrons will be in the second principal energy level? Because they are in this second period down from the top. So if you read this periodic table like a book, it's actually pretty easy to figure out the electron configurations. We did the orbital diagrams and the electron configurations all the way through the first 18 elements, stopping at argon. But today we're going to pick up at potassium and work our way across. And what will be different today was that we'll be working into this D block, which we haven't really worked with too much. And then we could possibly go into the F block, but that's going to be for a different day. To get electrons into the F block, we would need an electron or an atom that's somewhere in with an atomic number greater than 58. And that's a lot of electrons to place. It gets fairly tedious. So we're going to keep it simple today and start with the fourth period potassium element. Okay, so fourth period elements and beyond, you should have a worksheet that has a plethora of orbital diagrams. So we're going to start with potassium. Potassium has everything, and I'm going to highlight potassium right here. Potassium is right here. Potassium has everything that argon has, so therefore argon's in brackets, plus it's got 4s1. So argon is everything up through 3p, so 2 electrons in all of those boxes. Even way down there, it's quite a little bit off the screen, down there at the bottom, the 1s is off the screen. But what's interesting is it's got 1 electron in the 4s, so you should have this 1 up arrow in the 4s. If we go to the next screen, we'll see calcium. Calcium is this element right here, so it's still in the S block. It's the second element in the S block, so it'll be S2. Because it's in the fourth period, it'll be 4s2. So calcium has everything argon has, which is everything up through 3p, filled up, plus 2 electrons in the 4s. The next element is scandium. Scandium is the first element in the D block, but what's interesting here is this is not 4D, this is 3D. And this is what gets a little confusing because this first row of the D block, it's in the fourth period, but those electrons are going into the third principal energy level. So this is where the overlap begins. So scandium has all the electrons that argon has up through 3p. It's got the 2 electrons in the 4s like calcium, but then it's got 1 extra electron that has to go here into the 3d orbital, as you see here in this diagram. Titanium. Titanium is the second element over in the D block. So it has everything argon has, everything up through 3p. It's got the 2 electrons in the 4s, and it's the second one over in the D block, so it'll have 2 electrons in the 3d. So we write it argon, 4s2, 3d2. Chromium. Chromium is the element that is the fourth one over in the D block, so it will have 4 electrons. And notice Hund's rule. We have 1 electron going into each of the individual orbitals before we start doubling them up. So we would write this electron configuration as argon 4s2 3d4. And this pattern continues as we move on to manganese Mn. So manganese is the 5th element over in the D block, so it'll have the 5 electrons spread out, 1 in each orbital of the 3d sublevel. Again, Hund's rule. So manganese will have everything that argon has, plus the 4s2 and the 3d10. Iron. Iron is the 6th element over in the D block, so therefore it'll have 6 electrons in the 3d. And now we can start pairing up electrons. We can see the first pair happening in the first orbital of the D level. So iron now will have everything argon has, plus 4s2 plus 3d6. Cobalt. Cobalt has 7 electrons in the 3d sublevel, so we are going to continue now pairing up the electrons. We now have 2 pairs of electrons in the orbitals, 3 unpaired electrons. So we have for cobalt's electron configuration everything that argon has, everything up through 3p, but then it'll have the 4s2 and the 3d7. Nickel. Nickel has 8 electrons in the 3d sublevel. So again, we continue to pair them up as we fill up the 3d sublevel. So nickel has everything argon has, plus 4s2, 3d8. Copper, 9 electrons in the 3d sublevel. It's the 9th one over in the D block. So it has almost all the pairs made. It's got 4 pairs and 1 single electron in the 3d sublevel. So copper is everything argon has, plus 4s2, 3d9. Zinc. Zinc has 10 electrons in the 3d sublevel. So now the 3d is entirely full. All 5 orbitals each have 2 electrons. The opposite spins, you can see, if you recall, that is Pauli's exclusion principle, 2 electrons per orbital, and they must have opposite spins. But now we're not done with the 4th principal energy level. We filled the 3d, but there are still more elements to go in the P block. So now that the 3d is filled, the next energy level up is not in the 4th energy level, it's in the 3rd energy level, it's back in the 4th energy level. And so if we continue on to gallium, we'll see that gallium now has that extra electron in the 4p sublevel, so the 3d is all filled up. So gallium has everything argon has, plus 4s2, 3d10, and 4p1. And this pattern continues as we work our way across the P block of the 4th period. Germanium, 2 electrons in the 4p right here. So the electron configuration is argon, 4s2, 3d10, 4p2. Arsenic has 3 electrons in the P sublevel. Again, you're seeing Hund's rule, where only 1 electron goes into each orbital before we start pairing them up. So this is argon, 4s2, 3d10, 4p3 for the element arsenic. For selenium, we now have 4 electrons in the P sublevel. So now we can start to pair them up. We have 1 pair, 2 singles in the 4p sublevel, and the electron configuration for selenium is argon, 4s2, 3d10, 4p4. Continuing on, bromine is the 5th element over in the P block, so it'll have 5 electrons in the 4p. We can see that down here in the electron configuration down here, argon, 4s2, 3d10, 4p5, and in the orbital diagram we can see 2 pairs and a single in the 4p. The last element in this row is going to have all the electrons filled up in the 4p. So we have 4s2, 3d10, 4p6 beyond argon. And notice that we now have a full 4s and 4p. And when we have a full 4s and 4p, we know we have arrived at the column where we have noble gases. So this column right here, the noble gas column, has a full S and P sublevel, which makes these a very stable electron configuration and therefore non-reactive. There's no electron holes, there's no gaps, there's no single electrons or orbitals that need filling. So there's no reason for these elements to try to react, to try to swap electrons, and so they're inert. They don't react. Okay, and so these elements are gases, and they they're non-reactive, or you'll notice that, or sometimes some of the heavier neon gases are reactive, but very, very slightly. So I hope you see that this pattern could continue, and you could see how complex this could get if we were to continue on the periodic table going to the 5th, 6th, and 7th period. We're not going to do that. You can see that the pattern gets more and more complex and more overlapped as we continue. But if you read the periodic table like a book, you can really figure out the patterns that exist really without having to go through the pattern all over again. You know, you could pick any one of these elements, and for example, you know, if you picked iodine, iodine would have to be everything krypton has, but then it would have to have 5s2, 4d10, 5p5. It's really that simple. As long as you know the blocks, you know where the blocks are, and as long as you know that this block in the middle is pushed down by one row, it's really not difficult if you just understand the pattern. All right, that's it for this lecture. We'll see you in the classroom.